something to help us get the correct choice of u and dv for our integral is to use the acronym LIATE. Well, in this case, it's like a checklist of what we have, and whatever comes first, that's going to be our u. And the remaining part of the integrand is going to be our dv part. Okay. Also, let me write the formula for integration by parts, so we don't have to flip pages or scroll the screen all the time. Okay, so let's see. What do we have for a letter C? Integral of arcsine of x. Number one, L. Do we have logarithmic functions? No. What's next? I. What does the I stand for? Inverse trigonometric function. Do we have any? Yeah, so that's u equals arcsine of x. And well, what's the derivative of arcsine? All right, that's the trick. That's calc 1. What about 1 over the square root of 1 minus x squared dx? And then the remaining part of the integral, it's going to be our du, which is simply dx. All right. So u equals x. So we're ready to evaluate this integral by parts. Well, so let's see. U times v, that is arcsine of x times x, which is our, oh, actually, no, that's a dv, not du. That's dv, that's v, and minus the integral of v, which is x, times the quantity du, which is 1 over the square root of 1 minus x squared with respect to x. Alright? Well, before attempting to evaluate the second integral that we obtain, how about we do some cleanup first? That is, I'm gonna write this x in front of the arcsine to make this look like x arcsine of x. Well, actually, let me write it down here. X arcsine x minus the integral of x over square root of 1 minus x squared dx. Let's look at this integral. Any ideas on what would be a good way to compute this integral? Yes. The negative 1/2, but in terms of the setup, yes, u substitution, right? And then we will write this radical in terms of negative exponent, so it's easy to integrate. So u equals 1 minus x squared, du equals negative 2x dx, and then, well, so x dx means negative 1/2 du. So I'm going to go back to the integral. Number 1, I'm going to continue here. X arcsine x minus the integral of negative 1/2 du over the square root of u. And well, number 1, let's clean up the negative signs right here. Negative times a negative is going to give us a positive. And the 1/2 outside of the integral, and yes, this is radical in the denominator. Let's write it with rational exponent and then move it to the numerator with negative exponent. Well, because in this case we cannot integrate the variable while it's in the denominator, so that's an integral of u to the negative 1/2 du. Well, the rest of the problem is just general power rule. And plus 1/2 of u to the, well, add 1 to negative 1/2, that's going to give us 1/2 divided by 1/2. And notice how these two halves get canceled out. And this u to the 1/2 is the same as saying square root. And we can also back substitute for u, which is in this case 1 minus x squared, plus c, and plus c. All right? Any questions? I see some of you like a bit hesitant about any of the steps. All right, well, let's move on to the next example. Well, in some cases, we are required to do the integration the integration by parts more than once. And well, you'll see the pattern when we get to see this. Well, number one, so we have this this integral. Again, let's go with Liate, and let me write down the formula. So let's see, so u equals dv equals, well, so number one, L, do we have any logarithmic functions? Yes, no? No. Okay, what's next? I, inverse trigonometric functions, do we have any? A, what does the A stand for? Algebraic, do we have any algebraic functions? Yes, which one is it? X squared. So that's x squared. The remaining part of the integral will be the sine 2x with respect to x. So, and recall, the u is the one that gets differentiated, and the dv is the one that gets integrated to retrieve the function v, not to differentiate it again. Well, so this is du equals to 2x dx, and v is the integral of sine, which is, what's the integral of sine? Negative cosine, right? Negative cosine to x, and I left a space for that factor due to the mini g substitution. All right. Okay, so we're ready to evaluate the integration by parts, and now that we have all the setup, all the required pieces of information, well, so that's going to be u times v, in this case x squared, times v, which is negative 1/2 cosine 2x, minus the integral of v, which is negative 1/2 cosine 2x, times du, which is 2x dx. Okay? Well, before attempting to keep simplifying this or to evaluate the second integral, let's clean up the parentheses and the negative signs so we have a clearer view of what we're going to do. So number one, I'm going to write this negative 1/2 in front of the x squared. And then minus minus becomes a plus, and also check this out. These two cancels with that 2 over there because it's multiplying, the other one is dividing, and it's going to give us a simpler integral, well-ish. And well, we will be left with this x that I'm going to write in the front, cosine 2x. Well, let's observe the integral right here. Any ideas on what to do with this integral? Can we use a u substitution like we did in the previous examples and just get the result for this? What would be a good move here? Yes. Another integration by parts, right? Because in this case we have the product of two functions, and yes, we can have the product of two functions like this. All right, don't be confused with that thing about product of two functions, but because in this product of two functions it is possible to just use the u substitution, but not in this case. All right, so that's why I really don't call this like the product rule per se. We just relate it to the product rule of differentiation instead. Well, so that's one setup for the integration by parts. Let's do a second setup. U equals something, dv rather, equals the other part of the integral. And again, what's u going to be in this case? So if we go again with the acronym, what else? Do we have any logarithms? No. Do we have any inverse trigonometric functions? Any algebraic? X, right? And dv will be the remaining cosine to x dx. So u, or rather du, equals dx, and v equals 1/2 sine to x, because the integral of cosine is positive sine, but times that factor of 2, well, we divide by that. Alright, so let's go back to the integral right here. So negative 1/2 x squared cosine to x plus whatever we get from integrating this by parts, which again is going to be u times v, that is x times 1/2 sine to x minus the integral of v du, which is just dx. So, well, let's sort of simplify this. There's really not that much to simplify, by the way. Anyway, so this will be negative 1/2 x squared cosine to x plus 1/2 x sine to x minus 1/2 sine integral of sine to x dx. And while the integral of sine to x, we already did it when we set up the first integration by parts. So that's a negative 1/2 x squared cosine to x plus 1/2 x sine to x and minus 1/2 the integral of sine. But again, what's the integral of sine? Negative cosine times the negative becomes a positive. The 1/2 that we had from the setup of the integration by parts times the 1/2 from the integral cosine to x plus c. And well, we can very well simplify this 1/2 times a half by writing it as a 1/4. And that's final answer. Yes?
We're doing this second integration by parts and we're solving a negative in front of the integral. So we put another negative which makes it positive.
Like in this case, we had this negative right here. Yeah, because the integral of sine is negative cosine, but that negative times the negative from the outside of the hand becomes positive. Well, so the pattern here of how many times do we have to do an integration by parts, well, pretty much will be given away by the power the power of x that we have in our integral. For example, if we had I don't know, maybe let me make something up. The integral of x to the 7 e to the 5x dx. How many times would we need to do the integration by parts? 7. Well, that's going to be it's going to take forever, but well, just comparing the pattern, that's what we would do. All right, but of course we're not going to do anything this crazy. All right. Well, there's a special integral that you might want to be aware of. So integrals that contain the form e to the ax times either sine or cosine. Well, what about this kind of integral? It's a little dangerous integral, but well, in this case, treat the problem, or treat the problem as an equation. All right. Well, so Notice in the previous problems, this is what we did. Just go with the next line, equal, until we get to the final answer. This particular problem, we will have to treat it like an equation because, well, you'll see why in a minute. And you will see me writing the original problem constantly just so I can be consistent with the idea of treating this like an equation. Well, so number one, well, in this case, we're going to forget about the Liate thing because either actually this special integral, regardless of the order that you follow, it's going to work the same. It's going to work fine. So in this case, I'm going to set u equals the exponential, even though the trigonometric comes first in the Liate acronym, but I'm going to do the exponential first. So that's e to the 2x, and dv equals sine x dx. Alright, so, well, let's integrate, well, let's differentiate e to the 2x du to e to the 2x, and v equals negative cosine. That's the integral of sine. So we have the 4 parts that we need to start working with the integration by parts. And well, again, u times v, that is e to the 2x times negative cosine minus the integral of v, which is negative cosine, times du, which is 2 e to the 2x dx. Okay, one thing at a time. Let's like I mentioned, I'm going to write the whole problem because I'm treating this like an equation. The integral of e to the 2x sine x dx equal, so that's going to be, in the first place, it's going to be negative e to the 2x cosine x, negative times a negative, that's positive, the integral of 2 times integral of e to the 2x cosine x dx. And well, this integral, again, that requires integration by parts. In fact, it's the same, it's of the same form as the note, as in the note here, except that one of the factors is this time cosine, not a sine. Alright, so let's do that setup for the integration by parts a second time. So that's going to be u equals e to the 2x du equals to e to the 2x. From there, dv equals cosine, and v equals the integral of cosine, which is sine. Alright, so let's label this as number 1 and number 2 to denote that this is the first time that we did the integration by parts, and this number 2 is to denote that that's the second setup for the integration by parts. Alright, well, so let's keep going then. The integral of e to the 2x sine x, which is our original problem, equals, so far we already got this negative e to the 2x cosine x plus 2 times, and be careful here because that coefficient, I put it outside to multiply with whatever we get from doing the second integration by parts, which in this case we are going to use the setup in color green. Well, so let's get the parts. U times v, that is e to the x, or rather e to the 2x times sine x, minus the integral of v, which is sine x, du, which is e to the 2x dx. Alright, well, let's clear the brackets here. Let's simply also distribute the number 2 here. Oh, I forgot a 2 here. Alright, so let's see, let's distribute 2 times this whole term and 2 times the integral right here. Alright, so number 1 That's the integral e to the 2x sine x dx equals to negative e to the 2x cosine x plus 2 times the first term inside of the brackets and in this case positive times a negative is negative, and when we distribute these two, notice these two will get multiplied with these two that came from the setup of the integration by parts. That's going to become a 4 integral e to the 2x sine x. But did you observe something weird here? What did you notice about the result that we just got? So we're getting back to the original problem. What do? Set up another integration by parts in yellow and then do it again in green, doing that infinitely many times? No, we're not going to do that, because all we're going to be doing is generating terms, infinitely many terms, and that's not going to be the result. So that's why for this particular problem, I noted to treat it like an equation, because, well, what's the whole principle anyway? The whole principle here is that when you have like x equals to, I don't know, 7 minus 4x, try to solve this equation for x. Well, add 4x to both sides, cancel, and 5x equals to 7 and x equals to 7/5. So this is going to be exactly the same principle right here. In this case, we are going to treat these two integrals as like terms. I'm going to move this to the right, to the left hand side of the equation the following way. So I'm going to add 4 times the integral of 2x e to the sine x, e to the 2x sine x dx cancel here, and 1 integral plus 4 integrals, how many total integrals? 4. How much is that? 5 integral of e to the 2x sine x dx equals to negative e to the 2x cosine x plus 2 e to the 2x sine x. And all we have to do here is to divide both sides by 5 or multiply by 1/5. And this is the way around to this situation about falling into basically an infinite loop, right? So you don't want to do that. So the integral of e to the 2x sine x dx equals negative 1, when we distribute 1/5, that's a negative 1/5 e to the 2x cosine x plus 1/5 times 2, that's 2/5 e to the 2x sine x, and this is where we put the plus c. Alright? This issue only happens with integrals of this form. When we have an exponential multiplying either a sine or a cosine. Well, it turns out that this will be not the only case, the only situation. We're going to run into a similar situation later actually in the next section when we cover a special trigonometric integral. Well, you'll see when we get there. All right. In the meantime, questions about it? All right. So let's move on to the next. Well, evaluate the definite integral. So how do we evaluate a definite integral? So this is more like showing you the setup, because well, we already evaluated this integral before. So let's do it again, but now we're going to add limits of integration. So in this case, again, in accordance with Liate, which one is going to come first? The x or the sine? x. So u equals to x dv then will be sine 2x dx. The derivative of u will be du equals dx, and the integral of dv, which is v, is the integral of sine 2x, which is negative 1/2 cosine 2x. Okay? So we're ready to go back to the integral. And well, that's u times v, that's x times negative 1/2 cosine 2x minus the integral of v, which is negative 1/2 cosine 2x du, which is dx. Now, notice that the first term right here no longer contains an integral sign. This is already a result. So at this point, for the first term, we can go ahead and write the bar to show the limits of integration. So in this case, that's 0 to pi over 4. And well, let's keep the limits like this. Do not evaluate. Save it for the end until we get to the final result. So that's going to be negative 1/2 x cosine 2x, or if you prefer to compute them along the way, that's fine. But I usually prefer to wait until the end. So minus minus, that's a plus, the 1/2 integral of cosine 2x from 0 to pi over 4. Let's keep writing the limit. Alright, the integral is not new. We already did it a couple of times. Actually, it was the one that we did by parts twice. And this integral came up actually more than once. So that's a negative 1/2 x cosine 2x. The integral of cosine is sine 2x times 1/2 times the other half. That actually just becomes simply a 1/4. And in this case, you might want to write the bar for the entire function, pi over 4. And then, well, the rest of the problem is the usual upper limit minus lower limit. That is the fundamental theorem of calculus. So let's see, negative 1/2 pi over 4 cosine 2 pi over 4. Right, plus 1/4 sine 2 pi over 4. So that's evaluating at the upper limit. Minus, well, do we really need to evaluate the lower limit? Check this out. The lower limit, which is 0. What do we get if we evaluate the 0 for the first term? Did you see this factor of x? That's going to get the term zeroed out. And well, sine of 2x, that is sine of 2 times 0, which is sine of 0. What's sine of 0? 0. How about just big 0? Alright? That's fine. That's valid. To save some time on your writing. Okay? So what do we have? Cosine of 2 pi over 4, which is the same as cosine of pi over 2. But what's cosine of pi over 2? That's going to be 0, right? So this term is going to go to 0. And sine of 2 pi over 4, which is the sine of pi over 2. What's sine of pi over 2? 1. Alright, so that's 1. Well, so 0 plus 1 times 1/4. So 0 plus 1/4 times 1, that's simply 1/4. Alright? Question: what would this result represent? If we were to interpret maybe this result maybe physically, or something, or geometrically. Any ideas? Huh? The area under the curve. The area under the graph x equals sine 2x within the limit 0 and pi over 4. Alright? Alright, so let's move on to the next topic, which is trigonometric integrals. Alright, well, so here is where we will use every possible trigonometric identity. Alright, and but of course there's some guidelines to help us move on, you know, or at least get started with the problems, with the exercise. So we're going to start with the simplest of them. So in this case, we're going to evaluate powers of trigonometric functions. And well, you may have done some of them. I mean, when you had the integral of sine to the 117x times cosine x dx. Well, that's a very simple integral despite the big power, because that's just a simple u substitution, right? However, this time we're going to have other powers of trigonometric functions and combinations of powers of sines and cosines, and the remaining trigonometric functions, tangent, cotangent, secant, and cosecant. We will see at least one of every single function, all right? So, and again, in this case, these integrals will use u substitution after playing with, you know, with some of the factors here and there in the integrand. Well, so we have these general guidelines that you will see in pretty much every single calculus textbook or resource on the internet or other YouTube videos, etc. And well, number one, we have to observe if the power of cosine is odd. In that case, whenever the power of cosine is odd, save one cosine factor and use this trigonometric identity. And well, cosine squared equals 1 minus sine squared comes from the identity that you know by heart. You know, sine squared x plus cosine squared x equals to 1. Solved by one trig function or the other. In a similar way, we have that if the power of sine is odd, similarly in this case we're going to use this trigonometric identity, however, the other way around. Alright? But the trick is a little different when we have even powers of either or sine or cosine. Well, so when sine and cosine are even, we use the half angle, or what we usually call the power reduction identities. And well, the reason why we call this power reduction identities is because, well, a quadratic sine or cosine drops its exponent by 1 when we apply the identity. But what happens there when we reduce the power to linear, well, not necessarily linear, well, we duplicate the angle. Well, we're going to see examples of it. All right. I mean, of course, this is a lot of words, a lot of, I mean, this is like the checklist to follow, if you will. Let's have a look at one example. So for letter A, we have the integral of cosine cube of x. All right. If we were to evaluate this integral using the u substitution, okay, u equals cosine x du equals negative sine x dx. Well, we would be in trouble because unfortunately we don't have this factor of sine multiplying with the dx, which stands the u du part of the problem. So unfortunately we cannot go this route. So we have to think of something else instead. And in this case, well, we have some techniques right here. So number one, what is the parity of the power of cosine? Is that an even or an odd one? It's odd, right? Well, so we have an odd power of cosine. What do? Save one cosine factor and then use the identity. All right, so I'm going to use different colors so you can see what do we mean by saving one power. So number one, I'm going to rewrite this integral of cosine cubed as cosine squared x times cosine x dx. Okay? So I'm saving one of the powers of cosine as stated in the guidelines above. Well, from there, we are going to substitute cosine squared with 1 minus sine x. That is, this identity will be used here. Alright? So we will replace cosine squared with 1 minus sine squared. That is, the integral of 1 minus sine squared x cosine x dx. Alright? And well, from here we will create two separate integrals, or actually we don't even need to rewrite this as two integrals. Actually, we can set we can do the u substitution in this case, because yep. So u will be sine x du equals the derivative of u, which is cosine. And well, cosine x dx, it's already here to help as the du part of the problem. And what else are we going to have? Coming back to the integral, this will be the integral of 1 minus u squared, because u equals sine, this will be u squared, times this whole quantity cosine x dx, which represents simply du. And all we're doing is integrating this basic polynomial. Well, so the integral of 1, which is u, minus the integral of u squared over 2 of u squared, that's u cubed over 3 plus c. And we're essentially done with the integration here. Let's just go back, substitute for what we declare for u. That is sine x minus sine cubed x over 3 plus c. Alright? So in the end, everything falls into the u substitution, but we do that after playing with the powers of the trigonometric functions before we can move on through it. Alright, so what about the next problem? Okay, so letter B will be, well, this one will be a little long. Okay, let's get started. Maybe just a couple of lines here, at least a basic setup, and then we call it a day. All right. So we have the integral of sine to the 5th power and cosine to the 2nd power. Well, need to be very careful with these kind of integrals, because in this case your main focus is going to be the odd power of the trigonometric function, not the even power. I know it's as a first attempt it would be something like, okay, save 1 power of sine and use the power reduction formula right here. But there is a problem here. Notice if we did this, we would be getting factors of trigonometric functions of a single angle and a double angle, and we would be in trouble here. So we want to keep all the trigonometric functions of the same angle in this case, all right? Not combining angles. So let's take a different approach. So our focus here will be this the odd power. So number 1, this is the integral of sine to the 4th power of x times cosine squared x, and let's save 1 power of sine. All right. So let's see what about this. So on the previous page we got to one of the identities. Okay, no, it's not going to be enough space to show this. Well, so whenever sine is odd, replace sine squared, the remaining after saving one power, with 1 minus cosine squared x. However, we don't have a sine squared, we have a sine to the fourth power. So in this case, we're going to do this. We will rewrite sine squared x to the second power, because power of another power, this multiply the power, that's going to give us back the 4, and that's a cosine squared x times the factor of sine that we saved to set up the integral. Well, so the goal here is to convert all these signs right here in terms of cosine. Okay, let's keep going so you can see what I'm going to do. So that's integral of sine squared, which is 1 minus cosine squared, quantity squared, which is this term, times cosine x, or cosine squared x, times sine x dx. And well, notice what we did here is to write everything in terms of cosines, because once we set the u substitution for this, we can actually set u equals to cosine, and we already have the part that stands the du part of the problem. And in fact, we can already do that. Actually, it's not going to take too long. So that's going to be, well, u equals to cosine x du equals negative sine x dx. But be careful here, because sine x dx will be negative du. Well, doing the substitution, this will be the integral of 1 minus cosine x squared, which in this case will be u squared, the whole thing to the second power, times u squared times sine dx, but sine dx is negative dx. First of all, not dx, it's du. Let me take that negative outside of the integral to make our life easier, and in the end we're going to use that negative sign to change the sign of everything once we distribute this. Alright, so negative integral, squaring binomials. We need to square this binomial. There's a couple of ways to go about it. Number one, multiply with itself and do the foiling. An alternate form for this is to use the formula for expanding binomials, a plus or minus b, depending on the case. That's the square of the first term plus or minus 2 times the product of the first and the second term, plus the square of the second term. I think it's going to be shorter if you do it this way, but if you still prefer to do it the FOIL way, that's fine. Either way is fine. It's acceptable. So I'm going to do this. So 1 squared, that's 1, minus 2 times 1 u squared, 2u squared, plus u squared squared, that's u to the fourth, times u squared du. And well, let's distribute all the u's here, the u squared rather, over all these 3 terms inside of the parentheses. And that's going to be negative the integral of 1, or not 1 actually, that's going to be u squared minus 2 u squared times u squared, that's going to give us a u to the fourth, and u to the fourth times u to the second, that's u to the sixth du. And well, at this point we can use that negative sign to change the sign of everything. That way we don't get any issues with changing them at the end. So that's the integral of negative u squared plus 2u to the fourth minus u to the sixth du. And in this case we can just integrate the polynomial. That's negative u to the u cubed over 3 plus 2u to the 5th over 5 minus u to the 7th over 7 plus c. So that's the integral in terms of u, but we did a u substitution to make our lives easier, so we go back, substitute for it. That is negative cosine cubed over 3 plus 2 cosine to the 5th over 5 minus cosine to the 7th over 7 plus c. And I think this was perfect timing. All right.